So to summarize, estimation of parameters for simple linear regression using the method of least squares, we have defined the loss function, which is called the RSS, and the expression of RSS is given by summation of all the residuals square, where each residual is the difference between the predicted and the observed value. And so this is our loss function. This has to be minimized. And in order to minimize the loss function, we differentiate it with respect to the two parameters. This gives us two equations and we have two unknowns, and that's how we solve for getting the estimators beta naught hat and beta 1 hat. So from the first equation, when we solve for beta naught, we come to this expression where beta naught is given by y bar, the average value of y. This is summation of all the y's divided by the total number of observations, and this is summation of all the xi's by the total number of observations. So this is y bar minus beta 1 times x bar. And once we have the expression for beta naught, we substitute that in the second equation, and after some steps of algebra, we get this expression for beta 1. So using these properties, which again essentially comes from a little bit of algebra, one gets the final expression for beta 1, which is this numerator divided by this denominator. And we are going to use certain notations for these two terms. The numerator we are going to call as Sxy, and the denominator we are going to call as Sxx, where Sxy is essentially, so we are going to write Sxy as summation xi minus x bar times yi minus y bar, and in some sense it is giving how x and y co-vary with each other. Sxx, sorry, so Sxx is xi minus x bar whole square. So if I divide it by n minus 1 and take the square root of this term, the Sxx, we get the standard deviation. So Sxx in some sense is the variance of x, and similarly we can also define Syy as summation yi minus y bar whole square. So where Syy in some sense would give the variance of y. So beta 1 can therefore be written as covariance of xy divided by the variance of x. So this is our final expression for the estimator of beta 1. Let us now talk about the covariance term in a little more details. So as we had noted, the covariance term Sxy is nothing but the sum of xi minus x bar times yi minus y bar. I want you to note here that all these measures, Sxy, Sxx and Syy, they are all called central measures. That's because they are all with respect to the mean. So here you see it's the mean that's getting subtracted. So all these measures are with respect to the mean, and therefore these are called central measures. And now what can we note from this expression of Sxy? It is the degree of linear association between x and y, and the term linear is important here. So essentially it tells us how y varies linearly with change in x, right? And from this expression we also see that if there is a change in y which is consistent in sign with that of x, so if x increases, y increases, then that leads to a positive value of the covariance. Whereas if we have the sign of change in them opposite of each other. So if x increases, y decreases, then we have a negative Sxy, right? Now, I would like you to pause and think about what is the range of possible values that Sxy can take. Is there any limit to it? If you think carefully, the way we have written, Sxy really does not have any limits. So it can lie between minus infinity to plus infinity, right? We have not set any limits for this. What are some of the other things that we note? And some of the other things include some certain disadvantages of this term covariance. The first thing we note is that it is unit dependent. So if I express x, let's say x represents rainfall and y represents runoff. So if we take a data set of observed values of rainfall and runoff and we express the covariance while we are considering rainfall and runoff both in millimeters, then we'll get a certain value of Sxy. Whereas if I change the actual observed values of runoff from millimeters to inches, I might get a different value of Sxy. Although in reality, the nature of variation of between x and y, the nature of linear association between these two has not changed because my data is just the same, right? So Sxy is unit dependent. What is the other thing that we note about Sxy? The other thing we note is that even if the degree of linear association between x and y does not change, let's say if one of the variable changes. So if the variability of one of them becomes large, then Sxy will be large. And this therefore misrepresents the linear association between the two variables. So this is also another disadvantage of using the term covariance. So Sxy increases if variability in only one variable is high. We do not want that, right? We want a right measure of the linear association. We want a metric which will not be as misleading as covariance, right? So therefore, we would want to have a so-called standard measure. So we need to standardize Sxy. We need to standardize covariance, right? So that's why it's written Sxy is not a standard measure. The other thing worthy of noting here is that Sxy equals to 0 or tending towards 0 may not mean that there is no association. All it means is that there is no linear association. Like I said, the term linear is important. In order to overcome the problems of covariance, the expression for covariance can actually be standardized, and that standardized coefficient or the standardized measure is called the correlation coefficient, which is given by this expression, where instead of having just the numerator Sxy, we are also standardizing it by the standard deviations of x and y. So Sxy divided by Sxx divided by the square roots of Sxx and Syy, right? So this gives a standardized coefficient which is called the correlation coefficient, denoted by little r xy. And by definition, by the way we have standardized it, it can take a value only between -1 and +1. So that is the range of the correlation coefficient. Now remember, we had noted in the previous slide that correlation coefficient is 0 may not necessarily mean that there is no association between x and y. It does not mean that x and y are independent. All it means is that there is no linear association. And therefore, if you have a data set which is something like this is your x-axis, this is your y-axis, and suppose you have two samples denoted by red and blue, we see that there is in fact a very strong association between x and y, which means that if we know a given x, it is possible to predict the value of y, right? So there is association, but since the association is circular, we will end up calculating a correlation coefficient which is close to 0. So correlation coefficient close to 0 does not necessarily mean that x and y are independent. It means that there is no linear association between them, right? Let us look at some more examples. So here in the first case, we see that as x increases, y increases. And such an increase is also quite strong. The linear association, more or less, they lie in the direction of a straight line. So the linear association is quite strong. So one may expect a correlation coefficient which is close to +1. In the second figure, so here on the other hand, as x increases, y decreases, right? And therefore, one expects a correlation coefficient which is close to -1. And here, as x increases, in the third figure, as x increases, there is hardly any change in y. There's no pattern. If you fit a best fit line, it'll be somewhere close to a horizontal line, right? So here it will be like this. So in the third case also, there is no strong correlation. So therefore, our xy will be close to 0.